right, so our next topic is going to be about electronegativity and how it impacts polarity of bonds, and then how that polarity of bonds impacts the polarity of molecules. Our goals will be to define and differentiate bond dipoles and molecule dipoles, and then we'll determine if bonds and molecules are polar or nonpolar. So we've already defined electronegativity and dipole. Now we're going to take a look and we're going to define bond dipole. So this is the uneven distribution of electrons in a bond due to differences in electronegativity. And so whenever we draw this, our dipole is going to be drawn like this, where we have an arrow drawn kind of looking like a positive sign, and then to where the electrons are going. So fluorine has a greater electronegativity, so it's going to hog the electrons more. So if we take a look at the periodic table and we use our electronegativities like we've done before, we're going to determine which atom is negative relative to the other, and we'll draw our bond dipole. So for our first one, we have hydrogen, and then we have chlorine, and so we have 2.1 and 3. So our electronegativity difference is 0.9. If you recall, a polar covalent bond is going to be anything that's above 0.4 and less than 1.7, or 1.7 and less. So we have H bonded to Cl. The chlorine is going to be more electronegative, and so our bond dipole will look like this, and chlorine would be partially negative, and hydrogen would be partially positive. Why don't you go ahead and try for the other two? Right, so the last thing to define and look at then is what a molecule dipole is, and this will be an uneven distribution of electrons overall for a molecule based upon the polar bonds and the shape of the molecule. And so this is talking about, is the molecule polar or nonpolar? The example that's given is water, and so water has these bond dipoles here, drawn here, which means that hydrogen is partially positive and oxygen is partially negative. The charges don't cancel out, or the dipoles don't cancel out, and so because of that, this is a polar molecule that has a dipole or has a charge. Molecules that are polar are going to be asymmetrical, and they are going to have an uneven distribution of the electrons, but a lot of times also asymmetrical, or not all, a lot of times, all the time, also asymmetrical. And so asymmetrical means that they don't have dipoles that cancel out, so that's what we showed with the water, which is going to be bent shape, and then you have a trigonal pyramidal shape that is also going to be polar if the bonds are polar, because those dipoles do not cancel. You can think of this kind of as like a tug of war. If people were pulling on those ropes, would the central atom move? The answer would be yes for both of these. All right, so just because we have a bond dipole, meaning that we have a polar bond, does not mean that we have a molecule dipole or a polar molecule. So what this means is that if the dipoles cancel out, then we are going to see a nonpolar molecule. The way that we see that is that if we have a symmetrical molecule, and so we would have something that's linear, we would have something that is planar, or trigonal planar rather, and then we would have something that is tetrahedral. So if you have these shapes, assuming in this case that all the bonds are identical, meaning that they are bonded to the same thing, they're all bonded to hydrogen, or they're all bonded to fluorine, or whatever, then the bonds will cancel out if the molecule is symmetrical like shown. So our differences between bond dipoles and molecule dipoles. Bond dipoles, we're looking at electronegativity essentially. So this is electronegativity differences, and it's determining, are those bonds polar or nonpolar? So while these bonds are polar, this is going to be no net dipole moment, or nonpolar, and that's because it is symmetrical. As opposed to this one, where we also have polar bonds here, but we are also going to have a polar molecule because those bonds do not cancel out. And so we'll have a charge, and that means that it's going to be polar. I like to think of this as kind of a tug of war, and we can think of a bond dipole, if I compare my kids from whenever they were real little, if they were in a tug of war, they would be equal, right? Because they're the same size, so nobody's going to win. It's going to be an equal pool. Now, if my daughter Adelaide was paired up against Cam Hayward, my money's on Cam Hayward that he's probably going to win that tug of war. He's going to be a little stronger. I think he's a pretty nice guy, but still, he's going to be stronger. He's probably going to win. Okay? So whenever we see this, we're saying, is this a polar bond or a non-polar bond? Well, in this case, we know that it's going to be a polar bond. Cam Hayward's going to be negative. Adelaide's going to be positive because Cam Hayward's going to hog all of those electrons. And so you're going to have a bond dipole. If we put this into a molecule, though, what we find is that if it's symmetrical, so if we're having kind of a tug of war, if all of the dipoles are canceling one another out, then this molecule would be nonpolar. And this is our tetrahedral shape. Okay? Now, if we have a bent shape molecule, now this is asymmetrical, so this will be a polar molecule. It will be bent because we have all these bond dipoles that are pulling away, and so we're going to have a positive and negative end for our molecule. So let's go ahead and practice. We're going to draw structures. You can pause and draw structures if you can for water, CH4, CH3F, and CF4. We'll determine if the bonds are polar by looking at the electronegativities. So look at the difference in electronegativity. And then when we determine if there's a molecule dipole, we'll determine if there is symmetry or no. So here's an example of the molecules. We have water. You can notice that we have our bond dipoles drawn. Notice that we also have bond dipoles between carbon and fluorine, carbon and oxygen and hydrogen. Now, if we determine whether or not there's a molecule dipole, we are focused on is there symmetry or not. And so if we're looking at symmetry, what we find is that we have a molecular dipole, meaning that these are polar molecules because they have charges. In the case of water, oxygen is going to be negative or partially negative, hydrogens will be positive. And then the reason why this one here is polar is because of this. Both of these are asymmetrical. The asymmetrical part of the CH3F is going to be because of this bond that's going to be different between them. Okay, if we look at here, our next ones, these are going to be no molecular dipole. This is because they are symmetrical, and so they will be nonpolar. So despite the fact that they have polar bonds, they are still going to be nonpolar. If you drew CH4, which is what I asked you to draw, you would have a tetrahedral molecule, and so these bonds would be nonpolar bonds, and it would also be a nonpolar molecule. Now, whenever we talk about these, the reason why this matters is because we're talking about interactions. So polar molecules mix with polar molecules, nonpolar mix with nonpolar molecules, and whenever we look at like why does soap work? Soap works because it has a polar end and a nonpolar end, so it's able to interact with both water and grease in order to clean stuff up. And so that's why this matters, and that's why we bring this up in the first place. If you have any questions, please let me know.